Session of the day on markets, and our first talk is Henrik Nordström, who is going to tell us about estimating the future need of balancing power. It's 15 minutes.
Okay, so hi everyone, I'm Henrik and I'm a PhD student at KTH in Stockholm, Sweden, and I'm going to present the paper estimating the future need of balancing power based on long-term power system market simulations. And I think perhaps it will be a nice segue between the flexibility session and the energy market session. And I've written the paper together with Lennart Söder from KTH and with Robert Eriksson from the Swedish National Grid. So let's quickly go through the outline of today's presentation. I'm going to begin with motivating why studying the continuous balancing in a future scenario of the Nordic power system is an important topic. And then I'll get a bit more into detail of why this may need to be approached a bit differently in the Nordic countries compared to how it is approached in North American future scenario studies. I'll then briefly describe the model we propose in this paper. I'll present an example of results one can obtain with the model, before making some concluding remarks and presenting some areas of future work. So to begin with, I'm going to present one of the Swedish TSO's 4 different scenarios of year 2045 that we have worked with. And for these scenarios, the entire North European power system has been simulated with hourly resolution for 35 years of weather data. And as of a coincidence, an hour is also the length of the trading period in the Nordic countries at the moment. And in this scenario, the electricity demand is about twice as high as today in Sweden, mainly due to electrification of the industrial sector and the transport sector. The Swedish generation mix is 100% renewable, with 78% of the installed capacity being variable renewable energy sources. And there are also a total of 13 HVDC interconnections between the Nordic synchronous area, highlighted in pink in this figure, and external power systems. So in such a scenario, keeping the continuous balance between production and consumption will certainly be challenging, both because of the higher variability that comes with the fluctuating nature of wind and solar power, the higher uncertainty that comes with the difficulty to perfectly predict renewable energy generation and electricity demand, and also because there will be less inertial response from the power system due to the higher share of inverter-based generation. So today, the continuous balance is mainly kept by using reservoir hydropower resources located in northern Sweden and in Norway. But in this future scenario, the hydropower resources may not be sufficient to keep the continuous balance by themselves, or there may be more efficient ways to keep the continuous balance, like using, for example, demand-side flexibility. Thus, there is a need to further investigate how to efficiently keep the continuous balance between production and consumption in a future scenario of the Nordic power system. But these energy market simulations are not really sufficient for such analysis, as they only capture the hourly energy balance and not the continuous power balance that must be kept. And this brings us to the purpose of this paper, namely to provide a model to perform high-resolution simulations based on long-term energy market simulations, to then estimate how it may look in between time steps in these energy market simulations, which then allows for estimation of the future need of balancing power caused by variability and when components ramp at the end of trading periods. However, there are North American renewable integration studies, like the Eastern Renewable Generation Integration Study, that include 5-minute resolution economic dispatch with procurement of balancing reserves in a co-optimization. And this approach certainly seems sufficient to also consider reserves for continuous balancing in future scenario studies. But this approach is not used in the Nordic countries, and I will try to explain why it may be not super straightforward to implement this methodology in the Nordic countries, because there are some differences. So to begin with, in the North America, energy and reserve markets are cleared jointly, while in the Nordic countries, energy and reserve markets are cleared independently and at different times. So this basically means that solving today's market clearing problem in a future scenario in North America would also capture reserves. But applying this methodology in the Nordic countries won't really be in line with how the markets are cleared. Also, in the future scenario study in North America that I mentioned earlier, it is assumed that reserves are provided by keeping margins in online conventional generators, but in the Nordic countries, reserves can come from many different types of resources in a future scenario, and thus it's a bit difficult to consider reserves by just keeping margins in a certain type of generators in the future scenario studies in the Nordic countries. And also, when extending economic dispatch into higher resolution in North America, it is online conventional generators that are being redispatched to handle, for example, changes in wind power forecasts. But in the Nordic countries, this would instead be handled by changing the scheduled reservoir hydropower output. And as one then also must consider changes in the reservoir levels, modeling this in high resolution for a lot of different weather years would be extremely computationally burdensome. But of course, it's superior to consider both the energy market and reserves needed for continuous balancing in future scenario studies, and this should also be strived towards in the Nordic countries. So the question is how to reach there, and our approach to it is to first model the power system intra-trading period behavior to estimate how it may look in between time steps in these energy market simulations. Then to also model the uncertainties, like for example, uncertain wind power forecast and the outages of plants and lines to also capture the stochasticity in future scenarios. Then one can estimate the need of balancing power, and by analyzing the need of balancing power, one can then understand which volumes of different balancing services may be needed in different situations and which assets are available to provide these balancing services. And then lastly, one can finally create some understanding regarding how large margins to keep in which assets to consider reserves for continuous balancing when performing new long-term market simulations. And the aim of this paper is to deal with the first step, namely to create a model to estimate the need of balancing power caused by a mismatch of intra-trading period behavior of different power system components. So let's continue with a brief overview of the model we propose. So the model captures the need of balancing power in each of the 11 trading areas in the Nordic synchronous system with minutely resolution. And the model is customized to be applied to area-based models, but in the paper we also provide some suggestions how it can be modified to also be applicable to nodal models. So the main idea is to use trading period resolution simulation data of a future scenario represented by steps 1 and 2 in this flowchart to then create higher resolution data to estimate the need of balancing power per area, and this is represented by steps 3 and 4. And there is one main assumption that we make in this paper, namely that we assume perfect forecast of the energy from each component every trading period, as the purpose of the model in this paper solely being to understand how to model the power system intra-trading period behavior. And we divide power system components into 3 main types, namely controllable components, which are modeled to provide a constant power until the end of each trading period, where it then ramps to the new level. And the ramp rate then, of course, depends on which type of controllable component we study. And some examples of controllable components are HVDC interconnectors and reservoir hydro plants and conventional generators. And then we also have varying components, which are modeled to follow a cubic spline curve to somewhat capture the fluctuating nature of variable renewable energy sources and the electricity demand. And as we in this case study an area-based model where local fluctuations will be small compared to the aggregated area output levels, we think that this assumption is valid, but if studying a nodal model, it might be relevant to model, for example, individual wind farm fluctuations in detail. And to just illustrate what I mean with a need of balancing power, as you can see here, it is defined as the instantaneous deviation by the high resolution data we create and the step function that each component is assumed to follow in the energy market simulations. And by then adding up the need of balancing power from each component in the trading area, one can then obtain the total area need of balancing power. But then we also have AC transmission, which is modeled by a simple transport model aiming to net imbalances between trading areas. And by imbalance netting, I mean that an instantaneous surplus in one trading area can make up for an instantaneous deficit in another trading area. So in this example, if we study the uppermost figure, where imbalance netting is not considered, we can see that area 1 would end up with needing 100 megawatts of downregulating power, while area 2 would need 100 megawatts of upregulating power. But if considering imbalance netting, and assuming that transmission capacity is available, of course, none of the trading areas would end up with any need of balancing power. Continuing, I'll just show a very simple example of results one can obtain with the model. And here I limited the analysis to study results in SE4, which is the southernmost trading area in Sweden, which is somewhat interesting because it has 3 HVDC interconnections to external power systems. It has AC interconnections to neighboring trading areas, SE3 and DK2, and also 95% of the installed capacity is variable renewable energy sources in this scenario. And here we have performed a very simple case study just investigating how the use of the transmission reliability margin to net imbalances would impact the need of balancing power in SE4. And if you're not familiar with the TRM, it is the margin between actual transfer capacity of an interconnection and the transfer capacity reported to the market. So in reality, this margin will automatically be used to net imbalances, but if, for example, dimensioning balancing services for normal operations, one might want to reserve this margin in case larger contingencies would occur. And here you just see a very simple example of results one can obtain, but just from this figure, we can see that high peak needs of balancing power may occur at trading period shifts when a lot of controllable components ramp at the same time. The blue graph here, the peak at the end of hour 207 is almost as large as the current reference incident in the Nordic area. But we can also see that using the TRM to net imbalances helps a lot in peak shaving, as one can see the orange graph having a way lower peak than the blue graph. And from the figure, one can also see that using the TRM to net imbalances also increases the time when the need of balancing power is 0 or very low, by seeing that the orange graph inside the dashed squares here varies much less than the blue graph. So to finish, I'll make some concluding remarks and present some areas of future work. So to begin with, keeping the continuous balance of future power systems with large share of variable renewable energy sources will certainly be challenging, and by also considering this topic in long-term future scenario studies, the quality and usefulness of these studies will be improved. The model we propose in this paper captures the balancing need caused by variability and ramping of components. In other words, the balancing need caused by a mismatch of intra-trading period behavior of different power system components. And by using the proposed model, one is then able to make analysis regarding, for example, peak needs of balancing power, the energy needed for up and down regulation, different trading areas, how the need of balancing power varies in different situations, and also how different technical assumptions regarding the power system impact the need of balancing power. And in the simple case study I showed you, it was clear that assumptions regarding how the TRM is used to net imbalances actually had a large impact on both the peak needs of balancing power as well as how often there is a need of balancing power. And of course, we have a lot of areas of future work, and the main area at the moment is to improve the model to also capture stochastic power system behaviors like forecast uncertainties and outages, as this also will create a considerable need of balancing power in such a future scenario with very high need of variable renewable energy generation. Future work is also to investigate how the need of balancing power is impacted by moving towards a shorter trading period, as the trading period is planned to be shifted from 1 hour to 15 minutes in the Nordic countries within a couple of years, which means that controllable components then can ramp 4 times per hour instead of 1 time per hour. Future work is also to use the model to dimension future balancing services, to evaluate the balancing capability of different technologies, and then ultimately to understand how to consider reserves for continuous balancing when performing new long-term market simulation studies in the Nordic countries. And that was all I had, so thanks for your attention.
Thank you. Any questions?
Reza Shafiqah from University of Vasa, Finland. Many thanks for your presentation, and I have one question mostly related to the, based on your model, you can find out what how much we need the balance for the future.
Yep.
But how to provide this balance? What is the resources to providing it? Because I didn't see even in your future work that how to provide it. Is there any, for example, different flexibility resources to provide it, or you are going to make some new market structures for providing it, or?
Yeah, I briefly mentioned here that like to evaluate the balancing capability of different technologies. But I think that's an area of future work to like investigate, for example, how electric vehicle charging can contribute to meet the balancing needs, or that's one sort of flexibility and such to understand how to efficiently keep. But at the moment, the model just estimates the need of balancing power, and then we will see which assets do we have available to efficiently also provide these services.
Yeah, but for example, for the electric vehicle, it can be one of the source of uncertainty as well. So one of the needs of the balancing is itself the electric vehicles, if not controlled enough. I mean,
Yeah.
so for sure, the mixture of all the solutions, such as the forecast, the uncertainties, considering and in the long-term period, can be considered for the kind of accurate forecast of the, for example, it was for 2045, I
Yeah.
guess.
So sorry, I didn't really get your question.
Yeah, it was a kind of.
Yeah, just discussion. Yeah, but the nice thing is that you also can see at least how much power is consumed by electric vehicles in hourly resolution as well in the long-term energy market simulations that we base our work upon. So then I think we should make use and see which assets are available based on the long-term energy market simulations, and then see how to efficiently meet the needs. But of course, there's a lot of uncertainty in that.
Thank you.
Anjan Bose from Washington State University. I'm a little surprised by this need for more balancing power in a hydro-rich area. The issue here for balancing is not is in the future is not in those areas where we have lots of hydropower, and because that's what we use for balancing in the short term, in the seconds range. And so I was wondering, why do you think that the hydro reserves that you have, or hydropower you'll have in 15 years, 20 years is not enough?
I mean, I would say there are two main reasons. At first, most of the hydropower in Sweden is located in the north, but most of the consumption is in the south. So there's a lot of problem with congestions with north-south flows. So that may cause a need of having like balancing services in the south of Sweden as well, where there's not as much hydro. And also, I mean, perhaps if there's a lot of wind power, maybe one could maybe the hydropower resources could make higher bids into the day-ahead market and provide more energy, and doesn't have to keep as much margins for short-term balancing, if there are, for example, flexible resources that can contribute with the balancing services as well.
I have a quick question. How is the balancing power being remunerated?
At the moment?
Yeah.
Yeah, so I mean, there's different balancing services that, like FCR and the MFRR, and it's separate markets for those. And I think some of them are pay-as-bid markets, where they just activate the bids and get paid. But I think most of the markets are moving towards marginal pricing.
The reason I'm asking, is there a possibility there, or a problem with gaming, that people are kind of behaving in a way that will force, make you have to buy balancing power from them, and then they make more money?
Potentially. I don't know. That's future work.
Okay.
I haven't looked into that in detail.
We need to move
Yeah.
to the next.
Thanks a lot.
want to use this mic? Okay.
Okay, next talk, Nawaf Nazir.
Thank you. Yeah, thank you everyone for attending my talk. I'm Nawaf Nazir. And this is work in, I'm from Pacific Northwest National Lab. This is work in collaboration with Matt Salmasaki from University of Vermont. The title of the talk is Market Mechanism to Enable Grid-Aware Dispatch of Aggregators in Radial Distribution Networks. The problem that we're trying to solve here is if we have different aggregators and they want to bid flexibility into the wholesale market, what we're trying to figure out is how they can do that while satisfying the grid constraints, because these aggregators, even though they're bidding into the wholesale market, their resources, their flexibility is located in the distribution network. So how do you solve that problem? So just to motivate, I think a lot of people have talked about this, but with increased renewable generation, we have challenges around uncertainty in renewable generation that is brought up because of the increased penetration of these types of resources, which can also be seen, you can see that in either, within intra-minute variability, but also, variability in the load curve, as you can see in the duck curve of California. Over the years, the shape of the curve has changed. So there's a lot of variability, which is due to increased solar penetration there. So we have to account for, for this uncertainty in the grid. And this is only going to get worse probably as states like California, they want to increase the amount of renewable generation that they have in the grid. And the volatility in generation can possibly lead to violation in network constraints. So the solution to this could be, one of the solutions, we can tap into the flexibility that is available in flexible resources which are in the distribution grid. And this flexibility is basically composed of thousands of kilowatt scale devices. And what we can do is aggregators can sort of manage groups of these customer-owned devices, and then aggregators can bid that flexibility into the market. So we're bidding this flexibility into the wholesale market, but physically these resources, these devices, these aggregators are located in the distribution grid. So how do you solve this problem? Just to go over some of the existing works in literature, how they tackle this problem. Some works, they just neglect the distribution network completely and are not concerned with the constraints in the distribution grid. There's work around transactive energy frameworks and also around distribution locational marginal prices. But these are all kind of like looking at it from like a top-down approach where you solve an optimization problem and then you send this prices to different aggregators in the distribution network. The problem that we're trying to solve here is, how can we do this if we want to satisfy the grid constraints? So we need to coordinate aggregators in a grid-aware sense, so that they can participate in the wholesale market. So in order to do this, we borrow some concepts from internet. So if you have an internet service provider, and you buy a plan, you basically buy like a capacity plan, right? Some 50 Mbps or 100. And then the higher that your capacity is, you get higher speeds when you actually use that, when you use the internet. So there's the bottleneck is sort of there in the communication network, right? Where the network that provides you this capacity, right? So some customers might opt for, a higher kind of capacity, so they will be preferred over others. So those are the concepts we're kind of trying to borrow here. So in the same way, you can think of like the distribution network where you have flexible resources, and then we want to use those to provide services to the market. but the grid constraints are kind of like a bottleneck here because they kind of restrict how much the flexible resources can participate in the market. So you have these aggregators which have flexibility, and then you have, on the other hand, you have markets that they want to participate in, and the bottleneck is kind of like the distribution grid with all of its constraints, which limits how much each of these aggregators and these flexible resources can participate. So what we want to do in this work is basically how can we allocate this capacity, flexible capacity of the grid? How can we basically allocate a portion of this for different aggregators based on the bids that the aggregators provide for priority access. So if an aggregator wants a higher capacity of the distribution network, they can bid a higher price to use that capacity. And based on that, they'll be allocated a portion of the network capacity so that they can participate in the wholesale market. So this slide here shows the overall market architecture that we are looking at. We're looking at three entities here. We have the utility, also the distribution network operator, you can call them, and they are the owner or own the infrastructure of the distribution network. So they own the equipment, the lines, the transformers, and then we have the DSO, which you can think of it as sort of like an independent authority that clears the market if there is some congestion, so allocates flexibility to the aggregators. And then you have the aggregators that want to participate in wholesale markets, but need the distribution network to access that. So they will pay the utility to access the network capacity at whatever the market clearing price is. So here I'm just showing that architecture. So the aggregators, they bid into this market with like, okay, I want to have capacity P bid, which could be either for the whole feeder. I can use this. So the aggregators can bid into the market with like a capacity P bid, which that's the capacity that they would like to access, and this capacity could be either feeder level capacity, or it could even be different at different nodes, so nodal level, and also a price that they are willing to pay to access that capacity. And then the DSO, it gets all these bids for dollars, megawatts and dollars per megawatt, and it solves a problem which allocates the basically capacity to each aggregator, which is I'm showing here as P+. So that's the basic architecture that we're looking at. How do we solve that? We basically need to do sort of like a feasibility check, which basically means that, okay, all the aggregators, they basically provide the bids, the capacity that they want to access, and the distribution system operator simply has to check whether it can actually host that capacity or not, right? Is it feasible for me to host all of that aggregator capacity? So for reference, we're using a simple radial single-phase network. So how do we do that? We solve this optimization problem where I am solving for this, I'm minimizing the slack variable S, or kind of like I'm maximizing the capacity, because the slack variable just shows up in the power balance equation. So what I would like is that this slack SI to be 0. So when that is 0, that means this PI is simply equal to whatever, all the bids, the total bids that the aggregators are providing. And then obviously I want to make sure that under that condition, all the network constraints are satisfied. So I want to make sure that the voltages are within their limits, and the currents are also within their limits. So any transformer constraint, stuff like that, those things are satisfied. So if that satisfies, like if S will be equal to 0, then you can say, okay, the network can host all of this aggregator capacity. But then also I want to make sure that the power flow equations are also taken into account. So these are just the simple, not simple, they're very complicated, nonlinear power flow equations, just the dist flow model which is used for distribution grid. And so we can solve this problem. The issue basically comes up as the equations are non-convex. So we have a non-convex constraint over here, which links the currents with the power flows and the voltages. And as a result, this problem becomes non-convex, pretty hard to solve. If you wanted to, even just checking whether the aggregators can host the capacity or not. You could solve it by, let's say, you can use IP-opt, some NLP, but then you're not guaranteed whether the range that you would get would be feasible, right? When you get a range of solutions, you only guarantee like one point is feasible. You're not guaranteed an entire range. So to solve that, most of the works in literature, they use some kind of linearization approach to the power flow equations, or use some kind of a convex relaxation to do this. So what we did is we used a different approach. So this figure here just shows like a comparison of different techniques that are used to solve ACOPF. We have, let's say, the feasible set, which is non-convex, shown in blue. And then if you do a convex relaxation, which is basically like, an outer approximation. But if you did a convex restriction, or kind of like a convex inner approximation, you would be within the feasible set always. So that's the kind of approach that we took in this work. And we basically try to do is we try to fit a hypercube within this feasible set, right? And then these plus and minus would be basically the upper capacity limit, and the negative would be the lower capacity limit. So if we are able to find this hypercube within the feasible range, within this feasible set, then we would know this minus and plus points, and so we know what the range of capacity or the flexible capacity that the distribution network can host, right? So basically, through this convex inner approximation, or CIA, what we can do is we can provide guarantees on the feasibility of the solution, and we've shown this in our previous work that it's not overly conservative. And we can also provide guarantees that this region is always going to be feasible. So just to provide some preliminaries of how we do this, more details about this are provided in our paper. So you have this disk flow model, and you have the non-convex constraint. What we basically do is we find lower and upper bounds on this non-convex term. So the LB and UB are the lower and upper bounds. And we've actually shown that you can actually find convex approximations of these lower and upper bounds. Once you have the bounds on these nonlinearities, what you can do is you can use those bounds instead of the actual nonlinear terms. So what you can get is you get like new variables, p plus p minus, instead of actual p and q, which basically represent the upper and lower bounds on all your variables. And you can use those as proxy variables. And those, these are all, linear. So everything is now convex. So you can solve this problem in a pretty scalable manner. So based on this formulation that we have, we now formulate the market clearing mechanism, and we basically do it in 2 steps. So we do step 1, which is basically the network feasibility check, I showed earlier. In this case, we basically check, okay, can we host all of the aggregators bits? Can we host that on the network? If it's yes, then then there's no need for a market. You just everyone just all the aggregators can basically participate in the market without worrying about the distribution grid. But if there is some congestion in the network, then we basically go to step 2, which is basically the allocation of the capacity, and we solve this problem P2, which basically allocates capacity limits to each of the aggregators. So I'm just going to go through step 1, which is the feasibility check, which basically checks whether the aggregator capacity can be safely hosted. So it's the same problem that I showed earlier. I'm just trying to minimize this slack variable, or maximize the capacity. So I have my PG, which is just the nodal injection, which is the sum of all the bits of the capacitors. And then I have all the the constraints of the network, the power flow equations, and the limits on voltage and currents. But now what I do is I use my previous convection approximation, so I get these proxy variables for the current, and these proxy variables for all the P's and Q's and the voltages. So now this problem becomes scalable, and I can solve this in a scalable manner. And then I go to step 2, which basically checks that in case of congestion, what are the allowable network capacity limits which each aggregator should be allocated based on their bits. So basically we solve this problem where PMI is just the capacity allocated to each aggregator, which is the minimization of this cost here, which basically prioritizes aggregators according to their price bid, K. And subject to, this is just the power balance equation, the constraints on voltages and limits, and then again you have these inner approximation, which is basically just the same things I've shown again. So I can again solve this problem in a very scalable manner. So, and then I can calculate based on, once this problem is solved, I can get basically a market clearing price, which I choose to be the minimum price at each node, and I can calculate what the total DNO revenue is for each one. So I'm just going to show some simulation results. So in here, I'm going to have a feeder level pricing, where I have different aggregators with different prices, and they also provide their aggregator bids at different megawatts. Based on this, I can solve this and see how much each aggregator is allocated, flexible capacity, and then I can solve and provide what the clearing price would be at each node. So we can see that aggregator one is prioritized because it's willing to pay a higher price. And we also see that nodes which are closer to substation are also prioritized. In this case study, I just go over like different aggregator price bids for different nodes, but we get similar results. I can just skip through this. It's not that important. And finally, we also do a robust allocation where we are basically taking into account some uncertainty in the background demand. And we can do this again for the similar problem. So yeah, with that, I would like to conclude my presentation, and I'll be happy to take any questions. Thank you.
We have time for one question. Yes.
By Cui from Unreal. So my question, maybe I didn't understand it correctly, but so what's the point of the first optimization problem? It seems that you can only solve the second optimization problem. If the problem in the first problem is feasible, then you just get the whole capacity bid.
Yeah, so the first one is just the feasibility check. So if you get a zero solution there, that means that you can just host all the capacity. So you don't need to solve the second problem, and all the aggregators can just bid their flexibility without worrying about the network constraints. Only if there is some congestion in the network, then you go to the second problem, so that then you can prioritize. You can like say, okay, one aggregator can only bid in some range, another one can only go in some range, so that you take into account network constraints.
Okay, yeah, thank you.
Thank you.
And I think I can take another question. 2 more minutes, yes.
Okay, so Lina Royal, University of Wisconsin-Madison. So thanks, Noah, for the presentation. I was just curious, I just had this question about this. When you were saying that you're upper and lower bounding this nonlinear term, it seems like you are guaranteeing that you will not get violations of your inequality constraints, but are you guaranteed that you will always have a solution to the power flow equations?
Yeah, that's a very good point. I don't know how far off that was. Yeah, so like I'm showing here this hypercube that you fit. So in our work, we actually check a condition on monotonicity. So we show that if your constraints, which could be like voltages or currents or power flows, if those are monotonic with respect to the power injections, then within that range, you're always going to have a feasible solution. So you're going to have a solution at every point in that range. So even you're guaranteed the solvability also.
Okay, so then you get another condition.
Yeah, you
in
need to.
your
So yeah,
constraints.
I provide more details, but there's like you need to check a lot of conditions. The most important one being that the constraints have to be monotonic with respect to the optimization variables.
Okay, thank you.
Yeah,
Thank you again.
You are doing 2025. Hopefully this will work this time. Let's see. Yep.
Alrighty. Hi everyone. My name is Tom Perot. I'm from the University of Sydney, and I'm here to present my paper on power hardware-in-the-loop testing applied to a peer-to-peer energy trading framework. And I did this work along with Maxim Stojkovic and Gregor Verbic, who's up here in the crowd. And there he is in the little photo here as well. So the motivation for this work, I'm sure you've heard this many times before. So DERs are going to be a major part of future electricity grids. And in Australia, they're projected to form between 13 to 22% of the total installed capacity by 2040. And if they are not coordinated effectively, they can create a whole bunch of different network issues, which I have listed here on the screen. And this is obviously not new to anybody at this point. We're all kind of aware of what these things can do if they're not managed properly. So the big question is, how do we coordinate these in the real world to manage these risks? And so to do this, we decided to employ power hardware-in-the-loop testing, and this is just a really brief overview of what that means. So it basically combines the accuracy of hardware testing with the flexibility of software simulations, and it allows you to explicitly model complex hardware devices, such as inverters, directly into a simulation environment by interfacing it via like a voltage amplifier with a real-time simulation environment. And this often comes with two challenges. One is maintaining system stability, which is very important to actually run the simulation. And the other one is maintaining a high degree of accuracy. And these can often be conflicting goals, which I'll kind of talk about in the future. So towards this goal, at the University of Sydney, we designed this big test system to try to capture all of the dynamic behaviours of a typical residential prosumer. So this particular prosumer has a PV system, a battery system, with a commercial PV inverter and a commercial battery inverter, and also a load bank to simulate their stochastic load. And we've interfaced this with an RTDS via a Spitzenberger-Inspires voltage amplifier, which has a very good response time. And we have also modelled 4 other prosumers as Raspberry Pis to capture the communications requirements that we would see in the real world if we were to model this as an actual distribution feeder. And for the software environment, we just modelled a simple radial line with the 5 prosumers just connected at different buses and at staggered phases to represent what would happen in a real system. So you can see here, this is where the hardware prosumer is connected at bus 1. So this is household number 1, is this big system on the right-hand side of the screen. And the other 4 Raspberry Pi prosumers are the other 4 households further down the distribution line. And so between the hardware and the software environments, we exchange a set of signals. From the software environment, we obtain the bus voltage at this bus here. And then we feed back through the voltage and current measured by the power amplifier at the prosumer bus. So peer-to-peer energy trading, so this is a decentralized DER coordination strategy that has become, I guess, decently popular in research recently. And it allows prosumers to trade electricity directly with one another. And this comes with a host of benefits. So for example, there's improved incentives for prosumers to install these devices because they can get better cost savings as opposed to just a regular retail arrangement. They have reduced curtailment of DER generation because it tends to get employed more efficiently in a peer-to-peer framework. Lower grid losses because it encourages local trading. And there's less reliance or potentially no reliance on intermediaries, which raises the amount of cost savings that are available. But it does come with its own set of challenges. So there's a host of regulatory hurdles, for example. I'm not sure whether peer-to-peer is actually conducive with most regulatory environments we see today, so that's kind of an open question as to whether we'll actually see this implemented in the real world. There's the other question of what happens if a trade cannot be fulfilled at the executed amount. So let's say you wanted to trade somebody 3 kilowatt hours, but it turns out you only have 2.5 kilowatt hours due to forecasting errors or whatever else might happen. How do you handle that particular situation? And also, how do you factor in network constraints? And this is kind of one of the big issues with this particular coordination strategy. So peer-to-peer schemes are often run as continuous double auctions. Now, there's other ways to run them, such as through blockchain and direct peer-to-peer trading without a central auction platform. But we've decided to use a CDA. And so a continuous double auction, buyers and sellers essentially submit bids and asks to the market during each trading period. And the highest unmatched bid is, if it's greater than the incoming ask price, then a trade is executed, and vice versa for the lowest unmatched ask. And network constraints, they can be considered by applying marginal prices to each order based on the anticipated effect they could have on the network. And there was a great piece of work done in this reference 4, which was by Gregor Verbich, Archie Chapman, and Jason Guerrero, which tries to tackle this problem exactly. So if you're interested, I would recommend looking at that paper because it's a very good approach to trying to integrate network constraints. Okay, so here are the results of this particular simulation when we applied it to our power hardware in the loop environment. So again, we had the 5 prosumers on the distribution feeder. Energy was traded by this continuous double auction, or CDA, and we used the retail charges from a typical Australian retailer, and they listed in their standing offer that the feed-in tariff was 6.1 cents per kilowatt hour, and the peak time of use charge was 49.24 cents per kilowatt hour. This varies through the day, so I believe in off-peak it was about 10.5 cents a kilowatt hour. And you can see here, which is kind of the expected result of peer-to-peer, that all the trades were executed between this feed-in tariff rate of 6 cents per kilowatt hour and the time of use the time of use price, which fluctuated from 10 cents to 49.24 cents a kilowatt hour. And as a result, it brought savings to both buyers and sellers because you're selling at higher than the feed-in tariff and you're buying at lower than the time of use tariff. So this is an expected result, obviously. And so the expected annual value generated per household in this little very simple arrangement was $205.30, which is pretty modest, but I guess that's to be expected when you have just 5 households participating. And you can see here it was also very heavily swayed towards selling power because most of these households had PV systems and battery systems, and there was only one household that we modeled that was just a pure customer, which was household 4. So everyone was trying to sell to household 4. And as a result, there was a lot of competition for selling, not much for buying. And so this probably led to a suboptimal outcome in terms of savings. But there was still, a modest amount of savings to be had, which is good. And you can see here on the bottom right, this was just the incremental amount of savings per customer throughout the simulation period. I should mention that the simulation period was just a 24-hour period. And we used a basic PV profile that we obtained from a local solar company, I believe, and also load profiles obtained from a study done by Ausgrid in this particular part, in Australia, as our load profiles. Okay. So the main thing I wanted to focus on was the hardware performance. So did it actually execute the trades as we would have expected? And what actually happened when you applied this particular framework to a real system with real commercial hardware? And surprisingly enough, the hardware prosumer model actually met the dispatched amount with a relatively low median error of 5.45%. And you can kind of see that reflected in the graph on the right here. So it performed relatively well in that sense, but there was a big assumption here, and that's that we had to measure the power from the prosumer assuming that it was non-sinusoidal, and by using integration in real time. And I'll kind of talk about that a bit more in a second. It turns out if you do not use integration and you just use standard power triangle equations, you just get pretty nonsensical results, and this doesn't even come close to the amount that they agreed to dispatch, which is a potential big hurdle for this in real systems. Another interesting thing to observe is that we saw a big spike in reactive power import during periods when we were exporting lots of active power. Obviously, this isn't really ideal. We weren't intending to import a whole bunch of reactive power when we were, exporting to the grid to satisfy a market trade. So this is a bit of interesting behavior that was produced by those commercial inverters. And we believe it was mostly caused by the PV inverter, which was the SMA Sunny Boy. And so this is something that you'd have to take into account in real systems, this kind of unintended reactive power import that is just not part of what you're trying to actually export to the market. And the hardware prosumer bus voltage remained pretty steady, close to the nominal value of 230 volts. but it did experience these very high frequency oscillations, particularly during periods when there was lots of power export or import, which was, again, a bit unexpected, and we would have to kind of investigate further how this would impact a system with many of these devices. So the challenges. So the main thing that surprised us was that the PV and battery inverter had an extremely high level of distortion. And you can see here the PV inverter, which is the raw output was the blue waveform, is very vaguely sinusoidal, but extremely noisy. And this actually created all sorts of havoc when we were trying to run this power hardware in the loop simulation, because it made it go unstable because it was that much of a distorted signal. And you can see with the battery inverter, it was marginally better, but still had these very strange low frequency oscillations over time. And the combination of these two waveforms created a bit of a mess that caused the system to just collapse if we did not take any other action to make it stable. And so what we ended up doing is we decided to integrate this blue waveform and then try to extract exactly what the active power and reactive power were, and then basically through the RTDS create a nice smooth sine wave to pretend that there wasn't all of this distortion. And that was really the only quick fix we had at the time to make this thing actually run stably. Otherwise, in the first time step, it would just go unstable, the protection would trip, and we wouldn't be able to get any results. But again, this also has other ramifications, because power quantities, in order for this peer-to-peer scheme to actually even be feasible and for the exported power to match even to a close degree of accuracy the amount agreed in the market, you would have to use this real-time integration technique to get a value that closely matches it. If you just use a traditional approach where you just assume it's a perfect sinusoidal wave and just use your power triangle equations like this one, you get results that just aren't particularly even close to what you traded in the market. So this is a potential issue for existing commercial meters, because a lot of meters assume a perfect sinusoidal wave, and this is clearly not always true, especially with these commercial inverters that are currently flooding the market, especially in Australia. So we need to do some more work on exactly what kind of ramifications this will have in the future for these kinds of markets to be successful. So future work. So the first thing is pretty obvious. So we need to make some improvements to the system stability, because we wish to explicitly investigate the effects of this inverter distortion on an actual distribution network without having to do any conditioning of the inverter waveforms. And we have some ways of doing this. So we have identified, here's a little, I guess, depiction of what this feedback control loop looks like. And we have identified some places where we can reduce the time delays in this loop between the software environment, which would be this one, and the hardware environment. And this typically makes the system a lot more stable to those kinds of very rapid high-frequency fluctuations. So the first thing we can do is we can update the communication method between the power amplifier and the RTDS to use a fiber optic cable instead of just a regular analog connection. And that will reduce the time delay for that component down from about 20 microseconds to 1 microsecond. So that's a big difference. We can also reduce the simulation time step. So one thing we did in this model is we used 120 microseconds, which is a very large time step, but we can actually use a different model in the RTDS that only allows for a much smaller system to be modeled. But then you get a much shorter time step of 5 microseconds. So we'd have to use a smaller system. We can't model a very large distribution network, but we can at least gain some stability by changing this time step and having a smaller system. And we may need to look at having a feedback filter to gain more stability if these two measures don't prove to be effective. And then the other two, obviously we need to explore different network models. Everything is not always going to be a radial distribution feeder, so we need to look at all the different configurations of network models and how it could affect different arrangements of these DERs. And we need to study the effects of those communication delays that we modeled in our test bed, but we weren't able to capture in this particular simulation. So that's pretty much all I had. So yeah, anyone has any questions.
Questions?
Yep.
Ian Hiskins, University of Michigan. First thing, I'd just like to remind you that Queensland won the State of Origin series
Big
for
win.
these people from New South Wales.
No, I'm a Queenslander. It's all
Yeah,
good.
yeah,
It's all good.
So I won't pick on you too hard then. But why, if you're interested in peer-to-peer where the time constants are multi-second, why would you go to a hardware-in-the-loop situation where you're dealing in microseconds? The timescale decoupling is significant between the two.
Yeah, that's very true. So we mainly just wanted to see how commercial equipment behaved under one of these scenarios. And you're right, that's not necessarily directly related to the peer-to-peer framework itself, but we just wanted to see how, well, if you dispatched commercial inverters to meet a certain amount of power traded in the market, could it actually meet that requirement? And what kind of an error would you see based on most of the inverters that we may see in the Australian network today or overseas? And B, it was kind of a separate problem as to see exactly what kind of distortion and noise those devices would exert on the system, which we can then kind of investigate separately outside of the peer-to-peer analysis.
Any other question? Okay. Thank you.
Thanks. Hi, everyone. My name is Slayman. I'm a senior research associate at the University of Melbourne. And today I'm going to present to you a modeling and solution framework for the optimal integrated planning of electricity and hydrogen infrastructure for large-scale renewable energy transport. What's that? I was going to nominate myself. Thank you. Longest title award, I think. So not so much about trading or markets. So I hope you find this interesting. All right, so I'm going to start with the motivation, contributions of this work. Then I will talk about mathematical modeling before discussing the main findings of the work. And of course, a discussion of future works. So really the main motivation here is the opportunities that large-scale green hydrogen may create for maximizing the integration of variable renewable energy. So green hydrogen is expected to play a key role in decarbonizing many sectors, including the heavy industry, also transport. You can also export hydrogen to neighboring countries or other countries that are not that lucky in terms of abundance of renewable energy. So in effect, large-scale renewable energy hubs coupled to large-scale green hydrogen hubs can potentially unlock substantial economies of scale. But this is, of course, predicated on designing a cost-effective infrastructure. So to do so, you're faced with an important question, which is of whether VRE hubs, renewable energy hubs, and electrolyzers should be co-located. So this is another way of saying, should you transport electricity or molecules, right? And of course, you need to analyze the drivers and conditions that affect the investment decisions. So in the figures, the two figures are two extreme cases where on the one hand you're basically transporting renewable energy over long distances using electricity, be it HVAC or HVDC, and on the other extreme end of the options that you have, you can produce hydrogen locally, where in the location of renewable energy hubs, and transport that using basic molecules over pipeline networks. So centralized production versus distributed production. So if these are the two options that we have, why are we interested in integrated planning? Well, if you consider all the relevant technologies, in this case being HVAC, HVDC, and hydrogen pipelines, you can unlock superior designs, as you can see here in that one of the case studies that we have considered for the state of Queensland. Ian? I know. Yeah. So you can see this is the model produces a hybrid sort of infrastructure design where you have a mix of all the three technologies that everyone is looking into at the moment. Now I'll discuss that in of course, how we get to that model to produce this result. So quickly, I'll talk about contributions. What we're striving to do here is to capture all the essential physics that can impact the decision making. In this case, losses, of course, in HVDC or HVAC systems, or whether over the conductors or converter stations, transformers. Reactive power when you have AC systems. These are mostly not captured in previous works. Most previous works use MALT approximations that are really, in theory, can produce arbitrarily poor designs, right? So we also consider for pipeline networks, we consider quasi-steady-state modeling instead of a steady-state modeling, which can have a big impact on the sizing of pipelines and compressors, as we'll see shortly. So in effect, we're capturing pressure drops and line pack. Line pack, like I said, will play a big role in the sizing. For that, you'll require relatively high temporal resolution, and doing so, you can better capture the variability of renewable energy. So that obviates the need, for example, to use capacity factors in the sizing, which can, produce suboptimal results. We're also capturing compression losses and in the sizing of compressors. So quickly, the capabilities of the model. So in effect, we're trying to find the optimal integrated infrastructure planning design, which is the design with both the lowest investment cost and the highest profit from hydrogen sales. So the inputs, in this case, you have the investment cost for each option, the hydrogen selling price, of course, technical specifications of each option. You also need the water availability for electrolyzers and, of course, the profile of renewable energy forecasts. So as outputs, you'll get the total investment cost, total hydrogen sales, and hopefully the optimal location size and number of each option. And for free, for this particular work, you get the line pack profile. So in a bit more detail, we're minimizing the investment cost and maximizing the profit from hydrogen sales. And so this is, of course, subject to disjunctive constraints in this case that allow you to choose the best decision if your branch and Brown algorithm is tractable. So we also have, like I said, the physics of flow in electricity and gas systems, basically, and you have these nice coupling constraints that are linear. Of course, the disruptive constraints, you need binary variables to encode those. They're effectively big M constraints that are tight and big M constraints. So you're already in trouble without even considering the nonlinear constraints. The flow of electricity and gas, that's non-convex, as we have established. So you end up dealing with an MINLP that has a non-convex continuous relaxation. So this is much more difficult to solve than MINLPs that have a convex continuous relaxation. So for the latter ones, you can use outer approximation. There's relatively efficient ways of doing that from the mid-'80s. But for these ones, you need nonlinear branch and bound, maybe even mixed integer sequential quadratic programming, which still, not that mature in terms of scalability. So let's dive a little bit deeper into the component modeling, starting with electrolyzers, which use water and electricity to produce hydrogen through these two nice linear constraints. I should say that the first one, in reality, is quadratic, but it's a weak quadratic, so you can capture that with a linear function. So now for the capacity of electrolyzers, at the time of conducting this work, the largest single electrolyzer had a capacity of 17.5 megawatts, and it costs about $10 million. But in the future, there's a projection by CSIRO that says the cost of these electrolyzers might drop by 60% by 2035. And I think there's one of the manufacturers, I shouldn't name them, they're planning on designing a 100 megawatt electrolyzer in the near future. I don't know if they finished it yet. Now, in that electrolyzer station, we know that the output pressure from a typical PEM electrolyzer is about 3.5 MPa, right, at best. So for that, you'd need compression. You need compressor stations or compressors to boost that pressure to transmission levels, in this case, 10 MPa. So as you can see here, the brake power of a compressor is captured by this nasty non-convex nonlinear equation or constraint. But if you look closely here, well, we know that the intake pressure is 3.5. That's the output of the PEM electrolyzer. So you can fix that. You can fix that here. Now for the offtake pressure, effectively what we did is we took the average pressure across a pipe. We have 10 MPa, 3.5 MPa, took the average. You get this nice linear constraint without compromising the design that much. So your sizing would be sort of directly related to the flow rate across that compressor. Given given the amount of uncertainties and this planning problem, this is a safe assumption, I think. In the future, I will mention that in future work, we're actually planning on dealing with this constraint directly, without any simplification. So let's talk about the hydraulics of pipelines. So starting with, again, like I mentioned earlier, we use quasi-dynamic gas flow in pipes. So you can capture that flow dynamics with these, of course, the famous Weymouth equation, and the second one is the average pressure across a pipe. Luckily for both of them, perhaps not so obvious for the second one, which is the average pressure, but you can actually relax that. You can get a convex set if you relax that into any inequality constraint. We know that the first one, which is quadratic, you can get a convex constraint if you relax it into inequality. But the average pressure, you can also get a convex constraint, perhaps not that obvious. We actually proved that in one of our recent papers, if you want to go take a look. So the estimates of costs for pipelines, these were taken from the extended European hydrogen backbone, which was released in 2021. So now let's talk about HVDC systems. Working with the steady state power flow, you have, so the first constraint here basically relates the AC voltage and current to the active and reactive power injections of the converter. That's a non-convex constraint as well. The second one is the losses, captures the losses across the converter. And the third one is simply the pressure, the power across your conductor. These are non-convex. You can define new variables, W and L in this case. These are the squares of the magnitudes of voltage and current, and that will allow you to replace, you can replace the non-convex constraints at the top by convex counterparts. A mix of linear and rotated second order cones, as you can see here. So lastly, the HVAC systems, that's pretty straightforward. You can go from the polar form, OPF, to the W space. You still get a non-convex rotated second order cone, but you can relax that straightforward. You get a convex rotated second order cone constraint. So now, in effect, you end up with, like I said earlier, a much nicer MINLP with a convex continuous relaxation. This is in effect in MIQCP, everything's quadratic, which you can use. The barrier method, for example, is very powerful, thanks to self-scaled barriers from Nesterov. So you can use branch and bound. We tried linearized outer approximation, didn't really work that well because of the big M constraints. They're nasty. So So let's talk about implementation setup. We consider planning horizon 20 years, time resolution 30 minutes. That's in line with the RES forecasts of, from AEMO, which is the Australian Energy Market Operator. However, if you go with 30 minutes and 20 years, you have a massively large problem, obviously. So we use clever ways to reduce that into 4 representative weeks with k-means clustering and other stuff. We consider a hydrogen selling price of $3.23 per kilogram. It might, in Australia, the industry in Australia is very optimistic. They're aiming for a $2 per kilogram price in 2040, but that's Australian dollars. This is American dollars. Remains to be seen if this becomes reality. We use Gurobi, of course, for the MIQCPs. So 2 case studies. The first one is a canonical 2-node system, and we use that to basically analyze or study the effect of capacity, increasing the capacity, and the effective distance on the decision making. And the second case study it consists of actual renewable energy zones in Queensland, Australia, with 1 hydrogen offtake point, and we've got a distance of about combined distance of more than 1,500 kilometers. So let's start with the canonical 2-node system, starting with a 1 gigawatt capacity. We vary the distance from 200 kilometers to 1,000. And you can see for the 1 gigawatt capacity that HVAC actually remains competitive for up to 800 kilometers. But then beyond that, the high cost of cables and HVAC systems, and of course the reactive power requirements, that they tip the scale in favor of HVDC, which is in congruence basically with existing sort of studies on this. Now going up in capacity for 2.5 gigawatts, now the break-even point drops down to around 400 kilometers. Again, that's expected. Let's go to higher capacities here. 5 gigawatts is very similar to what we've seen in 2.5. Now, for larger capacity, 7.5 and above, you can see that these options are dominated by pipelines. And that's not surprising because pipelines have a large carrying capacity, and they become competitive at these capacities. Also, at that pressure, lower losses. And you have the effect of the line pack, which it is effectively a storage. And we'll see what effect the line pack has. I'm guessing my time's up. All right, so the renewable energy zones in Queensland. So as I alluded at earlier, we have a hybrid design. You can see that there's an HVDC system, 2 gigawatts. That's over 570 kilometers. And then 2 pipelines over a combined distance of 800. And of course, we have an HVAC system, a double circuit, 500 kilovolt, 3 gigawatt HVAC system over that. Over that 200 kilometer distance. So this here shows the profile of available VRE, accommodated VRE, and also the demand. And you can see the variability of renewable energy here. And you can also see that the demand profile, in this case hydrogen, varies over a smaller range compared to the profile of available VRE input. And this is due to the line pack. So that's the effect of the line pack that reduces that variability. And we have a transmission factor of about 99%, which means more than 99% of that renewable energy was transported and converted to hydrogen. This is the profile of line pack. And I should also point out that I also alluded at that earlier, that this is the impact of the line pack on pipeline and compressor sizing is really what distinguishes this modeling from previous works. So quickly, to wrap up, you can think of this work as a first step in developing a tractable integrated planning model with essential physics. Future work, we're planning on working actually on solving the original MINLP directly using our own sequential MILP approaches. We're considering modeling the battery storage and hydrogen storage and how that affects the planning. We're considering uncertainties, of course, forecast and demands, VRE, environmental, socio-political, all that stuff that might impact the design. And finally, I'll skip that. That's It's more technical for pipelines. Hydrogen is a small molecule, basically creates a lot of shear stress. So you need to account for maximum gas velocity, otherwise you have very high-speed molecules in your pipes. You don't want that. And with that, thanks for tuning in. If you have any questions. Misha.
Thanks a lot. Great talk. Well, benefit of hydrogen. Can you clarify how you come up with this cost?
Benefits of hydrogen?
Yeah, well, you have this...
You mean here?
Well, in the formula you had for optimization, it's a particular formula and you didn't explain what it is. In the optimization, you have this last term, if you can go to the slide. Yeah. Cost of, well, maybe not.
The hydrogen sales, okay.
Yeah.
I'm guessing here.
Profit, okay, profit, yeah. So what's that?
So here we're because we don't know exactly at this point what the hydrogen demand will be. We know that it's going to be a game changer in the future in terms of exports, also decarbonizing industry and the transport sectors as a start. So what we're doing here is we're trying to get as much hydrogen as we can from that system. So that's why we're actually maximizing the profit from hydrogen sales. But look, this modeling is parameterized. You can change the objective however you want. You can add operation and maintenance costs. You can add replacement costs. I mean, this is really just to demonstrate that you can do that. More about this is focused more about the constraints than the actual. So we're not giving the results to the government yet. That's.
Okay, fine.
Hi, I think this is a little hard talk to give at 6 o'clock, but I will try. I want to revisit the value of control and how maybe next generation control design could really contribute in a quantitative ways to decarbonization. A lot of people who are regulatory and policy people, they actually don't even appreciate this point. So opportunities are actually quite interesting, and I list them here. I don't want to go through details. I will leave the slides, but you can have this very highly dynamic distributed complex network with many decision makers, as we were talking about that, and you can do better control to do more efficient supply-demand balancing and delivery, both in normal operation and very important for efficient management of uncertainties in extreme conditions. So all that sums up to how much renewables you can actually utilize in the real system. And in order to do that, we have to actually revisit if today's control would work. And here I have just the sort of traditional sketch that we have of tertiary, secondary, primary control, that the way we think about control design now. But there is a whole slew of assumptions made that will no longer hold. Okay, I have to do that. That would no longer hold. I don't have a very good angle here. Yeah. So timescale separation really doesn't hold. We talk about equilibrium, but there is no equilibrium. You have fluctuations all the time. Linearized control of components also is when you have large variations. And so this is sort of self-explanatory why we need to revisit today's hierarchical control. So there is a big opportunity, but we have to sort of rethink the control. That's what I'm talking about. So if we go sort of deeper into hierarchical control, it fundamentally rests on temporal and spatial separations. And here, from whichever way one looks at it, you have these, we call them intelligent balancing authorities. These are basically portfolio of entities embedded into balancing authorities, or could be clusters of DRs, can be different things, and they interact very heavily in a spatial way within the bulk power system. And similarly, we have intertemporal, intertwining there between fast and slow and so forth. So there are all sorts of things here that we need to revisit. I did a lot of work on control and wrote textbooks, and if you start and think about this, everything has to be thought through again. So tertiary level control, we should have much more adaptive performance metrics to optimize over all controllable equipment. We now optimize over just generation settings and so forth. Then secondary control is full of questions. The Drup controls, we use them routinely, we talked about that. But I'm going to concentrate now on primary control. In order for tertiary control to be implemented, and tertiary control usually gives you the commands for meeting real reactive power on the load and keeping voltage at the generators and output of the generators. That somehow has to be implemented by secondary and primary control. But I want to point out, and maybe people don't agree with this, but if you look at the state of the art of primary control, this is a huge issue. How do you implement control? How do you control power and rate of change of power while maintaining voltages within the operating constraints? It really is a flat statement that you can support it for many hours. So tertiary control wants that implemented, but primary control may not do it. And in particular, when you start changing over large, operating regions, over large fluctuations, no equilibria, this becomes a big issue. So João Pecas Lopez is not here, but he pointed out yesterday something very important, the question of how the bulk power systems actually interacts with this is spatial complexity. And so we are thinking about, many people mentioned during their presentation about how is the distribution level or microgrids, how they're going to affect through the substations, they're going to affect the bulk power system. So we stopped and thought about this, and I've spent quite a bit of time on sort of thinking about, is there some easier way to think about this rather than just going technology by technology and so forth. So if you think about this, you actually have these bulk level balancing authorities, and we call them smart balancing authorities, intelligent balancing authorities embedded inside, and they all interact, right? And here is the example of one of them. So the thing that we've been working on for a long time is, can you actually formalize this notion of interaction variable between the different layers, temporal and spatial, and that's what I would like to talk about. So long ago, in the 90s, Shel Liu did his PhD thesis at MIT on something very interesting, and I didn't realize till very recently how far-reaching that actually was. So if you think about just linearized frequency dynamics, that's what he did, and you have you look either at the control areas or look at the generator itself, you draw the boundary around the module. There is internal dynamics in terms of its own state variables, but there always exists linear combination for the linearized model, linear combination of internal states, which we call interaction variable, and that exists, it can be shown, comes from the conservation of power around the module. And it has absolutely beautiful properties. You can compute it locally based on your internal states, and also rate of change of that interaction variable, I'll show you a little bit more later, is zero when you disconnect from the others. So it naturally lends itself to decoupling and distributed things as long as you manage these interaction variables. So this system here, usually what you see, there are fast variation, let's say power outputs out of generators, but these interaction variables are slower. They are net imbalances. And so what is nice for scaling up is in this transform state space when you start thinking about interaction variables which have properties of net power basically in balance. You can zoom in, you can zoom out, and manage complexity of very complex systems depending on what question you're asking. And so there was work on that. I gave some references there, but what's interesting, we were talking about centralized versus decentralized, at what level of granularity you control your different parts of the system. So here it's shown, depending if you control component, you control frequency very quick, one way. If you control the subsystem, control area, you get different response. If you control, the entire system or subsystems, you get different frequency regulation. And so depending on what quality of performance we want, we get very different things. And you can use the interaction variable to make this scalable. That's a big payoff in this transform state space. And again, here, no time to go through this, but another student did, if you have typical fluctuation here in solar, for example, at one of the loads, you can control just the interaction variables at different layers and regulate frequency. We call that enhanced automatic generation control and so forth. And the communication requirements are nothing excessive. They just in terms of interaction variables between the different layers. Okay, now things get very interesting, and this is more recent work. So I talked about linearized frequency dynamics, and because of power and energy conservation law around the module, you always have these. Now what happens when you have multiple time scales, you have all these reactive power dynamics, electromagnetic dynamics managements with reactive devices that we have with power electronic storage? Can you actually generalize? And this is more recent work that a couple of people at MIT did. Actually, it's not fairly straightforward. It took a lot of time to show that you can do this zooming in and zooming out exactly the same way as you did it for linearized decoupled frequency dynamics, real power frequency dynamics, except now the interaction variable, and I don't have time to go through this, there is a lot of references we've written on that. You have the interaction variable is instantaneous power and the rate of change of instantaneous reactive power. So it's a two-dimensional vector. And Rupamati Jadivada, who just finished her PhD thesis, my co-author, she actually made this slide, which I think is telling a lot. So when you're on a very fast time scale with power electronics and electromagnetic oscillations, this is what happens with control. This is why we are tripping. So somebody mentioned you have controllable voltage source behind RL circuit. That's your inverter-based control, right? And the question is, how do we control this? Well, you have dynamics of the inverter. That could be inertia of your machine if you want. And that is here mismatch between power that you want to consume and power that's controlled out of this source. And typically, you control the controllable source, assuming that mechanical power is fixed. And however, because of the delays in control, you end up having some offset in power. And that offset in power starts doing all sorts of interesting things that we don't understand now yet. So depending on what sampling delay you have, depending on this time constant that you have in the inertia internally, you get different types of oscillations. So what people usually do to avoid that offset, they add some damping. And then, depending on what inertia is, you can have, in particular when inertia is negligible, which is, we talk about this all the time now, it's resources with small inertia, these oscillations grow. What is very interesting is that if the average value of this offset because of delay, for example, in power, is non-zero, you can have slowly creeping instability, slowly at a very fast time scale. And we don't understand this at all. So how do we model this without getting bugged up into different power electronics technologies? So how do we do it simple way? Example of what I was talking about, that was a sort of the classroom example, but what you see here is your household with everything that you control power, for example, that's coming out of the of this controllable equipment in the household to either supply or send power to the rest of the system. And the real problem is, this is fundamental problem with our primary control. You control what's coming out, assuming that there is no dynamics in what's coming in. And here is the design for example, for microgrids and DRs interconnected, but it's just an example. So how do we make it feasible to return to these interaction variables again? So after a lot of work, there were 2-3 PhD students worked on this the last 5 years on how do you actually avoid this problem at that fast time scale. If you go through generalization of these interaction variables, the only thing that happens different when you go into coupled thing is not just instantaneous power has conservation, meets conservation, but also rate of change of generalized reactive power balances. We always write these DAE equations where you say real power balances and has some dynamics and then it's subject to algebraic constraint. Well, at this time scale, that's not true. And I remember somebody was showing that, I'll get there in a minute. So we now generalize this interaction variable so that you include, first of all, we have to differentiate these things for over a given time horizon, how much energy they produce. So that's a candidate for this energy variable. But then it goes further. The instantaneous power has to balance. So you have power, instantaneous power, not real power necessarily, as a state variable in this transform state space. What's very interesting when it comes to these fast time scales that the problem is not all power produced can be delivered fundamentally due to the mismatch in rates at which this energy conversion is processed in connected components. And because of that, you have to actually have this third component in the interaction variable, which is rate of change of either real power or reactive power. So if you go through a lot of math, sorry? Okay. If you go through a lot of math, you can actually show that this generalization, generalized interaction variable, which is instantaneous power, rate of change of generalized reactive power, is sufficient to characterize these models in a very abstract, very elegant way, zoom in and zoom out way. Somebody was showing this afternoon these problems with reactive power looking very weird. I think it was Gregor's student. They do look that way. That was not the numerical error or anything. But to capture it, you have to have this generalized reactive power, which is basically, you're on the port is voltage times rate of change of current minus current times rate of change of voltage. John Wyatt, I strongly recommend looking into this paper because it is generalization of the reactive power in that time scale when you have to worry about electromagnetic part. So I'm not going to take too much of your time, but basically just to convey that there exists this notion of interaction variable now. Rate of change of interaction variable between the components is instantaneous power and rate of change of reactive power, generalized reactive power. And you don't have to do linearization. You don't have to do PQ decoupling. The same definition holds. So this takes us into much easier mathematical problem, just to say this, Shmuel, sorry. If you are in this transformed energy space, at the high layer, you have stored energy and rate of change of stored energy. You can show that that dynamics depends on those aggregate variables and also rate of change of interaction variables. A lot of structure. And so we have been doing a lot of work now on basically doing control in this elevated energy space with interaction variables so that the controllers at the primary level are just aligning the imbalances between sent and received interaction variables. And you can go through a lot of proofs. It's a linear problem. It just simplifies the power systems problems without assumptions. So, sorry. Just one more thing, I think it's quite important. So if you can use these interaction variables two different ways. And it's relevant to answer if it's centralized or how much centralization you need. First, some students did work where you do this competitive control in this generalized energy space, which means I have flywheel, and if I have disturbance on the wind power plant, I will cancel all of those disturbances so the rest of the system doesn't see it. If everybody does that, everything is fine. Very expensive, very conservative. Much harder thing to do in terms of interaction variables was the question of, and this is absolutely essential for these low inertia problems. You have the fault, and you have low inertia wind power plant, say. You can actually increase critical clearing time for that fault just by having, at the very fast time scale, the fax device absorb that electromagnetic energy. This is the time scale at which we are now talking about with power electronics. And just one more slide to show. So that all took us to the following thing. Can you have this simple framework in which you have minimal information exchange between things and still guarantee the performance? And these dotted lines, they're actually these interaction variables at different layers, and zooming in, zooming out at different time of granularity. So that's all I had to say.
Thank you.
Yeah.
Okay, so I suggest that all the
questions later.
speakers
Yeah.
come down, and we have 1 minute, 20 minutes to have,
I don't know how.
Please sit down. We'll have some discussion.
Okay. I'll keep this one. Okay.
Okay, so Ian Hiskins, University of Michigan. At least one question for Suleiman. What is the trade-off between electrical transmission and gas pipelines? So I know that in the use of hydrogen in natural gas pipelines leads to brittleness and failure of pipelines. So does that mean a shortening of the life? Because transmission is, people know that transmission lasts forever kind of thing, but hydrogen pipelines, are they a shorter lifespan? How do you build that in? And the other trade-off is you presumably bury pipelines, but you have an environmental pushback against transmission lines, so there's those trade-offs that one needs to think about as well. And the other aspect in the formulation, in Queensland there's a lot of talk about pumped hydro, so Kidston is being built, there's other pumped hydro schemes. So would that impact, or how would you take that into account in the formulation as well? Thanks.
I can answer the first question, but the second one I wasn't clear on what you're actually trying to ask.
So the first question is trade-offs between transmission and hydrogen pipelines. And the second one is building pumped hydro, so storage, bulk storage, not battery storage, but bulk hydro storage into the scheme. I guess would give you greater utilisation of the electrolyzers at night time when there's no solar, and that would certainly seem to impact on the relationships there. So I wonder how well that can be integrated into the formulation.
So to answer your first question, the main reason why pipelines are competitive and they're considered as a viable option is they have the inherent storage capability in the line pack. So you can use that to your advantage, and depending on the scale of the network, your demands, your RES capacity, you may not need hydrogen storage or storage at all. So that's why they're competitive. You mentioned embrittlement when you inject hydrogen into natural gas systems. That's a more, like you said, a short to medium term solution in the transition, the decarbonization roadmap. I actually did some work on that. For those of you who were at PSCC 3 weeks ago, we looked into the transient behavior of the gas flow in existing natural gas pipelines when you have hydrogen, and how you track molar fractions. I believe there are some trials at the moment in Germany with, if I'm not mistaken, correct me if I'm wrong, Germans here, 5% volume hydrogen. Embrittlement, look, Future Fuels, CRC in Australia, they've done a lot of work on this. They found out that up to 20%, you're still okay in terms of hydrogen.
You're talking 100%, right?
That's right. I'll get to that. Yeah. With 100% hydrogen, that's a completely new pipeline, right? So you would be designing it with embrittlement in mind. So you wouldn't have that issue. That's why there's an interest in this. So, I mean, the first thought was, yeah, we can inject hydrogen into the gas network. It might work. But the second one was like, if we're designing a new infrastructure, why not chuck in pipelines in the mix and design them specifically that are resilient and sturdy against embrittlement? So I believe that this technology does exist. It hasn't been rolled out yet. I don't know if there are any pure hydrogen pipelines installed at the moment. I'm not sure. If anyone wants to weigh in, you're welcome. So the second question you asked about pumped hydro, I guess I may have addressed it indirectly. Pumped hydro, like I said in the future work, we're currently actually considering storage, battery storage, and hydrogen storage, whether underground storage, salt caverns, engineered hard rock caverns, all these options are on the table. And also Future Fuels is working on this. They have released a big report on for Australia, at least, on where the viable options are for underground storage of hydrogen. So we're going to actually collaborate with these guys to include these options in the model.
Hydrogen's after you, if you want to fully utilise the electrolyzers, so that big expense of electrolyzers, right? If you're using solar, the sun only shines for half the day. So then you've got the electrolyzers not doing anything for the other half. So the storage needs to be electrical storage to utilise that capability at night time. So it's different form of storage.
Jochen Stiasny from the Technical University of Denmark. Just to follow up quickly, so okay, with these energy islands in Denmark, actually there is the opportunity to design kind of from scratch a new system in a way. So for that, I guess it's perfect. How do you see it when we have an existing system, and especially when things become operational at different times? So pipelines are much quicker to construct than HVDC links, especially in Germany, I can tell.
Yeah, that's correct. They're easier to install. I mean, you said existing pipelines?
No. I mean, or to what part?
No, you did mention new infrastructure.
So if you have existing infrastructure and parts of your model come, or they can come maybe 5 years apart into operation. I
Right.
think, how would you integrate that into your model? Because that changes, I guess, all the investment decisions that you make.
Right. Yeah, I think if I understood your question correctly, you're asking whether you can, in the interim time, maybe design an infrastructure that can leverage your existing infrastructure before you phase it out, and then you'll have your new one for the long term. Is that what you're asking?
Yeah. Oh, yeah. All right. The time until everything is in place that you plan, how does that play into your modeling? Okay, we can.
Let's take it offline.
Mr. Chertkov, University of Arizona. It's again to Sulaiman, so I don't know, Shmuel, if you want to.
What?
Well, it's to. I have another question to Sulaiman. If anybody else wants to entertain other mem. Yeah. Yeah. Well, it's kind of technical, but so Line Park. Well, I can. Okay. That's fine.
Quickly, maybe, if you want.
Sure.
All right.
Actually, I have a question to you. I'm trying to understand why you cannot formulate the allocation of the distribution wires or capacity the same way we do with energy. In other words, by having the aggregators bid energy at the different locations. Isn't that kind of the dual of what you're doing?
This thing is not coming off.
So in this problem, we're not actually. I'm only like calculating the range in which the aggregators can operate under. So they're not like bidding into the market. The DSO is just allocating them some capacity range in which they can work. So basically, we don't want.
But isn't that their bids for that capacity going to reflect somehow the value of the energy that they want to transact?
It reflects the sort of like how much they're willing to pay in terms of like if they have maybe cheap flexibility, they'd be willing to pay more for the network capacity, right?
So, I mean, we could have done, I mean, this was discussed 20 years ago when we decided how to deregulate the transmission system, and some people suggested to essentially have people bid for capacity of the grid. So it seems like kind of deja vu all over again, that you are trying to translate I mean, essentially your problem can be solved by creating distribution locational marginal prices, and then you'll know exactly how much the transmission components are worth.
Right, but I think the only difference here is that in order to get the distribution locational marginal prices, you would have to solve an optimization problem at every market update, right? We're not doing that. We're basically for making it simple for the aggregators in the sense that they only have to worry about a range in which they operate under. So once they know that, they just like figure out just to be in that range, otherwise they can do whatever.
But that's established to be inferior to having frequent distribution locational marginal prices.
We were trying to figure out how we can do this in a simple way while taking network constraints into account. So, so we are borrowing concepts from the transmission capacity. Yeah. Thank you.
Okay. Jochen Stiasny from Technical University of Denmark. To Maria, so about these interacting variables. It's clear that different levels of the power system, I can imagine that well. How would you, within a level like the transmission level, you could have like different zones. How would you design these zones, or how does the shaping of these zones affect kind of the usefulness of the, well, not the usefulness, but the effectiveness of these variables? Could you elaborate on that?
I understand. So I showed that plot where depending if I control generator itself, I get one response per frequency. Or if I control area, I just respond to the entire area control area, or I get another response in the system. So that's how it affects, right? So you are going to get different settling times. This is all distributed. You're going to get in different overshoots, but at least you have provable performance. You know, it was very hard thing to communicate in short time, but what is absolutely fascinating that you can scale it up spatially, and also this most recent work is that if you add the rate of change of generalized reactive power, the price to pay is that your components or modules have to control these interaction variables. So where it gets complicated, at the interface you know what to control because you're controlling formulating linear problem. But then you have to map it inside, you know, if it's inverter control or it's generator control. So we actually even teach this in the course, you know, how do you go from that to controlling the physical variables and what are the parallels which the way you control it now. So I think it puts it at the level where we can argue that this is minimum that you have to exchange, and given the boundaries and organization of the industry. Yeah. I don't know if that answers. Maybe we can talk more. Yeah.
Maybe I'll ask another question. Still the discussion about, I was intrigued by the presentation about Sweden. First of all, the question that Anjan Rose brought up about that you have all this hydro in Norway. Why can that be used somehow to do that? But the main question that I have is that what's the barrier in Sweden to actually having a kind of a locational balancing market for balancing energy, rather than kind of doing it sideways?
I don't know really, to be honest. I think maybe it's just old decisions. I mean, it's been a lot of discussions like regarding having like nodal prices versus zonal markets as well, but I don't really know if there are any clear barriers. I just think that the entire market for both balancing and energy has been based on having these trading areas. And
yeah, but you know, like here we have two settlement systems or you can have intraday markets. Yep. But the bottom line is that you have the day ahead forwards, and then you fix the infeasibilities with the balancing market. The problem is that it's the same resources that are going to provide the balancing as the resources that trade. So there are all kinds of opportunities of gaming that you can manipulate your infeasibilities in order to be paid by the balancing market.
Well, can I make a comment on that? Because we had a visitor, his colleague.
Sure.
And so I learned a little bit about that Nordic system. So what happens is that you have this north-south and west-east frequency oscillation. I forget exactly at what frequency level. And so it is not just about locational scheduling. You know, there is this is why I'm so excited about what we are talking about. It's really this inter-area dynamics that's happening that market doesn't really capture. So I forgot 0.8 hertz or something, you know, that you lose a component and then you have these oscillations, and the market doesn't even know that happened. And so my question for you was, how do I connect that inter-area oscillation with intraday market? Because you were arguing at the beginning that if you simulate the intraday market, you can say something about frequency.
Not really about frequency per se, but...
So why are you simulating the intraday market? Why are you simulating the intraday market?
I mean, it's just to estimate what needs of balancing services there may be in future scenarios, to estimate what gaps, like what imbalances there may be. I'd say it's not really, we're not simulating frequency directly, but rather which volumes of services may be needed to cover power imbalances.
But you are doing intraday balancing so that you don't have frequency problems. That's the only reason why you're doing intraday, right?
yes, in reality that will be, yeah.
Isn't the problem that perhaps the granularity of the zonal system is not fine enough to actually make sure that the trades are feasible? That's what you end up with all this imbalancing that occurs. Like before Sweden became 3 zones or whatever, they had this big problem that there was this, because the consumption is in the south and all the hydro is in the north, and they had these problems with trading with Denmark, that the Danes were buying all the cheap energy from the south, and then they were trying to put an artificial constraint on the transport, and the European Union actually took them to court and prohibited that. So that's why they had to split Sweden into multiple nodes, and I think that now the problem occurs the same, that you really have intrazonal congestion that creates all this problem with the balancing.
But I think an important thing is that I want to say that one real important question on that granularity is that, and I worked with Danilo the whole summer on this, you don't know which zone is creating the problem. Well, because it's... go ahead.
Yeah, I mean, yeah, both like which zone is creating the problem, but also like in which zone is the balancing resources located as well, and are we able to like, I mean, you must consider like both where the imbalances are created, but also where the resources are located to handle these imbalances.
Well, my question is, could you solve the problem by simply splitting the south into finer zones and then avoid some of the imbalances?
I think one of the answers that you gave was that Sweden also had different zones for balancing issues. I mean, in the US, we have some balancing areas that about half of the US, like MISO, whereas we also have balancing areas which are only like 2 gigawatts. So you can manage it. I think your point that, and also the other thing that these smaller utilities do quite often is to buy balancing power. And the only question then arises is what is the transmission restriction in being able to get power to do your balancing? And I think whether you solve it with zonal prices or LNPs, or you do it by building some more transmission, is a toss-up, right?
But our imbalances here, you know, we kind of solve the issues of congestion. So the imbalances are not due to congestion. The congestion is handled in the day-ahead market. Most of the congestion is handled to the nodal pricing. They mixing the congestion of temporal deviation with the congestion.
Right. Well, balancing won't. I mean, balancing is a real-time thing. You can't have congestion on balancing. The frequency will die. So you have to have if you have agreements, whether it's long-term agreements or market agreements to buy balancing power, then the transmission has to be there.
Okay.
I can just make a final comment.
Yeah. It's not a question, it's a comment. I guess the problem of Sweden is mostly related to the type of the hydropower. It's actually run-of-river, I guess, not storage of the power mostly in Sweden. At least it will be similar to Finland. So there are not lots of storage of the power, so we can use it for the balancing. It's just similar to the uncertainty of wind, so we have the uncertainty of the current of the water. So it can make some problems and avoid to use it for the balancing, am I right?
That's not really, I mean, most hydropower is reservoir hydropower in Sweden.
So it's not the river and run
no,
of the river?
No, it's not a lot run of the river. I mean, I think the issue is that I would say the main purpose of like having other balancing resources is that then the hydropower plants don't have to keep margins to have balancing energy or balancing power available. So then they could like commit more and bid higher bids into the day-ahead energy market. And I mean, hydropower is a very cheap resource, right? Which maybe then could avoid more expensive generators needing to commit in the day-ahead market instead.
Thank you.
Okay, I think